Hi Statistics 1 class. So this is a short video. We're looking at a couple of questions. First of all, one from exercise 4.5, question 3, which was asked this morning and we didn't have time to cover it. So we're covering again relationships between events, looking at mutual exclusivity and independent results and that sort of thing. So that's our first question, and I've got it written up here. We are told that the probability of event A is 0.5, and we're told that the probability of event B given event A is 0.6, and we're told the probability of the complement of B, in other words the probability of not B, is equal to 0.7. And we are wanting to show that the complement of A, not A, and B are mutually exclusive. So how are we going to go about solving this? Well, what we want to show is that there is nothing in here, that this little section here, there's nothing. Okay? They're mutually exclusive. In other words, there's nothing that is not A and also at the same time B. So how are we going to show that? Well, let's see what we do know. We know that the probability of B must be 1 take away 0.7, since not B and B must add up to 1. So the probability of B must therefore be 0.3. Okay, and we know this formula here means probability of B intersection A over the probability of A. This means B and A. So, we're also told that this is equal to 0.6. Now, this gives us the information that B intersection A is going to be equal to this probability, 0.5, multiplied by this, because we can get this by itself by multiplying both sides by the probability of A. So 0.6 times 0.5 is 0.3. Now, if we fill this in this Venn diagram here, we know that B intersection A is 0.3. And we know that A in total is 0.5, so this must be 0.2. And in addition to that, we know that there's nothing in this. Everything that is B is also A, because in total B has a probability of 0.3, and that's also B intersection A is 0.3. So everything that's in B is in A, which means there's nothing in there. And outside of B there, and outside of A must be 0.5 as well. Okay, I think we have everything we need. Given that everything that is in B is also in A, that must mean that B and not A is mutually exclusive, since everything that's B is also A, nothing that is B is also not A. Formally, we need to write that in this way. If they're mutually exclusive, we know that the probability of A complement union B, if it's these are mutually exclusive, it should just be simply the probability of complement of A plus the probability of B, and that is indeed what we find. The probability of A, not A, union B is in fact equal to the probability of not A, which is 0.5, plus B, which is 0.3, and the probability of not A and as well as B, so adding those two together, not A is this, and this is B, is also 0.8. So we've proved this, they must be mutually exclusive. I hope that helps you with the first question. And now the second question that I would like to do with you is from your textbook, page 89. It's a past exam question, and it says, this is number 13, it says, Jamie is equally likely to attend or not attend a training session before a football match. And if he does attend, he's certain to be chosen for the team, which plays in the match. If he does not attend, then he's got a 0.6 probability that he will be chosen for the team. And we have to find, first of all, the probability that Jamie is chosen for the team. So probably that's just like, we need to draw a tree diagram. So, first of all, he attends training, or he doesn't attend training. So I just go not training. And I think it was a 50-50. It was half chance either way that he attends training. But if he attends training, there's a certainty that he gets picked for the team. We'll say chosen. C, chosen for the team. So it's certain. So this branch is 0.5 times 1, or 0.5. If he doesn't attend the training, he still has a 0.6 probability of being chosen, and therefore he must have a 0.4 chance of being not chosen. So we can work out our branches. This is 0.3, and this is 0.2. And if we add them all up, it should add up to 1, and it does. Yay, we're on track. Okay, so we have to find the probability that he's chosen. So the probability that he is chosen for the team is equal to this plus this, or 0.8. That's the first part so far, so easy. The second part to the question is to find the conditional probability that Jamie attended the training session given he was chosen. So, probability that he attended the training given that he was chosen. Now we're going to need our formula that we've hopefully learnt off by heart by now. It's going to be the probability of T intersection C divided by the probability of C. T intersection C means both trained and also chosen, which is this bit here, trained and chosen, 0.5. Over the chance that he was chosen, which is 0.8. So you have 0.5 divided by 0.8, which is 0.625 probability. I hope that helps you get a little bit more how to do these conditional probability and mutually exclusive ones. If you are having trouble with any other questions, please email me and I'll see if I can get a video up ASAP. Good luck, guys. I hope this goes well for you.